सिराज सर, आपसे अकाउंट आपके अकाउंट से स्टार्ट हो गया?
Hello, is I'm audible, sir?
सिराज सर, यस।
Thank you very much, sir. Arun sir, is I audible?
Yes, sir, audible.
Yes, sir, audible.
Thank you very much, sir. Good evening, one and all. I am Dr. M.D. Sirajuddin, co-coordinator of this FDP. I welcome you all on behalf of Bageshwari College of Engineering to this 6 days faculty development program. Without wasting much of your time, it is my pleasure to invite our speaker of today's session, and I would like to introduce him, Mr. Pathan Karimullah sir, Senior Software Engineer at Concentrix, Hyderabad. With over 15 years of rich industry experience, Mr. Pathan sir has specialized in designing, developing, and deploying enterprise-grade applications using Java, J2EE, Spring, Hibernate, and microservices. He has strong expertise in CI/CD pipelines, Docker, Kubernetes, GitLab, and cloud platforms like Amazon Web Services, Azure, and Google Cloud. Mr. Pathan sir is also an Oracle Java SEB certified programmer, and he has successfully worked with leading clients including HCI, IBM, and so on. He brings proven skills in end-to-end development, debugging, deployment, and so many microservices. We are truly honored to have him with us today to share his insights on quantum cryptography and its impact on cybersecurity in the digital age. I welcome you, sir. Thank you very much for joining us. Thank you very much. So over to you, sir. Karimullah, sir.
Yeah, thank you, Mohammed Sirajuddin, introducing me on behalf. Yeah, hi everyone. This is Pathan. As everyone knows, Mohammed Sirajuddin given the overview of my profile. Yeah. So today I'm just going to share the knowledge on this cryptography and its principles of quantum cryptography. So basically, before going to start, I just wanted to give you a high level background of cryptography. So as we know, like to share any confidential information over the internet or in the digital world, so we have so many techniques to share confidential data over the internet or in the digital world, right? So cryptography is one of the most popular way of sharing the secure, sharing the sensitive information over the internet, which we call them basically. And here earlier we use different techniques to share the sensitive information between the source and destination. So there are a couple of ways to do it. So one of the most popular way is cryptography. There are a couple of ways we can achieve this using like symmetric key and asymmetric key cryptography and hashing and digital signature. So everyone aware of the symmetric key cryptography like we used to do it using AES advanced encryption standard. For example, if we have a like in every microservice architecture, we just need to connect to the couple of applications, a couple of tools like Kafka, Redis, DBs, and all. So not only the programming, so we just need our programming has to be communicated with the different tools. So for every tool connection, we need a connection string, right? So that connection string is nothing but a sensitive data. So if that connection string is revealed, then hacker or someone third party authorities can then access the data and then they can view and then alter the data in the DB or in the other tools like message exchanges like Kafka, other brokers, right? So in order to secure the data, we have these techniques as of now, right? So for example, if you want to connect to the MySQL DB, so the DB is having username and password. So whenever the junior developer comes, he doesn't know about it, and then he just hard coded the username and password to connect to the DB by using any programming language. So that is explored to outside. So if something happens and if something goes wrong, and then the hackers or someone third party who is not having authority, then they might use or misuse the information that is there in the DB. So that is it is important to secure those kind of informations in IT industry, right? So for that reason, the cryptography is one of the most popular technique to secure our information using either AES or RSA or by hashing or by digital signature. So these all are we are actually now we are following, but when it comes to quantum computing, so quantum computing is more means like the classic the quantum computing is more faster than classic computing which we are currently in. So the quantum computing is not implemented full-fledged as of now, but in future quantum computing would implement and then that will impact our this whatever the techniques which we follow to secure our information, right? So to overcome that, we just need to work on the quantum cryptography aspect. So I'm just going to present quantum cryptography related principles and things how we can achieve and secure our information. So I'm just sharing my screen. Just let me know once you are able to see my screen. So hope my screen is visible to all of you guys. Someone raised their hand. Hope my screen is visible, everyone. So here I'm just presenting the screen. Just let me know once you're able to see my screen. Suraj,
Yes, sir. It is visible, sir. Please continue.
yeah. So here this is quantum cryptography principles and techniques. This is we can get how we can achieve securing the confidential information using quantum cryptography. So we know already there are a few cryptography mechanisms which we are currently using, but this quantum cryptography is just related to the quantum computing and how we can secure sensitive information over the internet or digital world. So here are few agenda items which I am going to discuss today. So what is the fundamentals of quantum cryptography, and what is the difference between quantum and classical approaches when it comes to the cryptography, and quantum key distribution. It's a major the major key item which we are going to discuss, and implementation and challenges while implementing. Okay. So the first is, what is quantum cryptography? Quantum cryptography is a security approach that leverages the principle of quantum mechanisms to create theoretically unbreakable encryption systems. So earlier we discussed already. So there are a couple of approaches to do a cryptography. There are so many mechanisms which are available and currently we are following, but this is also one of the approach to create theoretically unbreakable encryption systems. Unbreakable in the sense, so like public key, private key sharing and accessing the confidential information. If there is a possibility to get the public key, private key by the hacker, but here we just overcoming the existing whatever the implementation technology mechanisms which we have. So there are some possibilities the quantum computing will break the secure communication. So here in the quantum cryptography, we just enhancing whatever the problems which are there and existing, and then we just wanted to overcome using these quantum cryptography principles. See, unlike traditional cryptography, which relies on mathematical complexity, quantum cryptography bases the security on the fundamental laws of physics. So, this is quantum cryptography is completely based on the fundamental laws of physics. So, we know already the quantum theory. The quantum theory will follow the photons and neutrons, electrons, which transmit through a medium. A medium is nothing but a fiber optic cable or something, some other medium, and it will make a strong connection established between source and destination. So here also in quantum cryptography, the fundamental laws of follow the fundamental laws of physics. And the primary goal is to create a communication channel that are secure against any computational attack, even from quantum computers themselves. So the primary goal of this quantum cryptography is to create a communication channel that are very secure against the attacks, even from the quantum computers. So everyone knows about quantum computers, right? So which are currently the most of the companies are investing, and even India also having the separate channel to invest implementing quantum computers. Google, IBM, and many Fortune companies are investing their feature in quantum computing, because so quantum computing is more faster than the classic computing which we currently doing. So how it works means, I hope everyone knows, like the classic computers will have only zeros and ones, like for example, if you write a program, a sample program, it will convert the compiler will compile the code, and then it will translate that human readable language into their machine level language, and then it will execute the instructions which are being written in the program, and then it will give us the result, right? So in quantum computing, that is something different. So we know, like we have an identical state of 0 and 1. So when 0 means off and 1 is on, and when it comes to quantum computing,
Pathan sir, you are muted. Please unmute and continue.
okay. So okay. Sorry, I just done that mute button. Was forget to answer. Okay. So am I audible now?
Yes, sir, you are audible, sir. Please continue.
Yeah. So quantum cryptography principle and techniques. This by using this cryptography principle and techniques, we can achieve like securing confidential data, which is transmitting from source to destination. Okay. So here there are today's agenda is about the quantum cryptography fundamentals, and there are few fundamentals which we need to follow when implementing the quantum cryptography. And we can see like what is the difference between quantum versus classical approaches, and quantum key distribution. This is a major part which we are going to discuss in quantum cryptography, and implementation, and what are the challenges while doing this quantum cryptography. This is the main agenda which we are going to discuss today. Okay, so the first part of quantum cryptography is, as we discussed earlier, the quantum cryptography is also a mechanism to what you can say, to create a communication channel secure against any of the attack. So the quantum cryptography is a security approach that leverages the principle of quantum mechanisms to create theoretically unbreakable encryption systems. And unlike traditional cryptography, which relies on mathematical complexity, Quantum cryptography is basically security and the fundamental laws of physics. You know the fundamental laws of physics. So everyone knows. I hope everyone knows the quantum theory. The quantum theory, inside the atom, what molecules we have, and there are protons, electrons, and yeah. So basically, the quantum cryptography will also follow the same fundamental laws of physics to transmit the data or to transmit the keys or to secure the information which is sensitive. And the primary goal of this quantum cryptography is to create communication channels that are secure against any computational attack, even from quantum computers. So I hope everyone knows about quantum computers, which which may change the computing world, and the most of the Fortune companies already investing their future in quantum computers to deliver high speed of solutions. Like in classic computer, if for example, if it takes 20 minutes to do a job, and in quantum computers, it will take only one 1 second or 2 seconds. So that much faster are quantum computers, but there are limitations like the classic computing. We can perform from anywhere in the world, and there is no restriction. It can be like we can operate from anywhere in the world. But when it comes to quantum computing, so there must some restrictions. So there is a vast building blocks for quantum computers, and we just need to maintain that computer in a minus minus degrees of minus degrees of you know, minus degrees of temperature. So here in the quantum cryptography, we should follow the principles which are proposed. And also, quantum cryptography is not just an incremental improvement. It represents a fundamental different approach to information security that could revolutionize how we protect sensitive data in ML systems. Everyone knows about machine learning also. So there are not only in ML, when it comes to digital world or the information technology, everywhere we just have to deal with the sensitive information, not only in ML systems. So everywhere we just need to deal with the sensitive information. That sensitive information matters. So, for example, if any of the developer in an organization or any of the programmer wants to implement any of the application, like the medical or government related or any government sector related projects or any other telecom or any of the product, for example, any of the product suite is going to implement. So they have to deal with the sensitive information. For example, there are a couple of microservices in microservice architecture, and those microservices has to communicate with each other, and those microservices has to be communicated with the different tools like um, RabbitMQ, the message exchanges like RabbitMQ or this Kafka or MySQL DB or Postgres DB, any of the DBs or any of the tools when the microservice wants to connect it, then we just need to have a separate connection string for it for each of the tool. So if for suppose if we just hard coded the connection string username and password to connect to the DB or connect to the Kafka, connect to the Redis or connect to the RabbitMQ. So if something a hacker or someone from someone hacked that username and password, they can misuse the sensitive information or present in the DB or in the messaging queue, right? So for that reason, we just need to implement a solution that will give us a strong, secure communication channel between source and destination. So why quantum cryptography matters? Suppose to quantum security and information theoretical security, ever dropping detection, future proof systems. So post-quantum security provides protection against attackers from both classical and future quantum computers, which can break many current encryption standards. And information threatening security offers security based on the laws of physics rather than computational complexity assumptions. And ever-dropping detection. So this is the most powerful feature in quantum cryptography. Ever-dropping detection can detect interception attempts through quantum mechanical properties. For example, as a source and destination, we are trying to share the data using quantum cryptography, for example, zeros and ones in the byte format. So in between, if we have any hacker trying to manipulate the photons which are transmitting from source to destination, so quantum cryptography will detect the position of particular the byte is changed, and that can be alerted to source and destination, and they can revoke that key, and then they will try after some time, or they will create a new key to exchange the information. This is the most powerful feature in quantum cryptography, ever-dropping, eavesdropping detection. And the feature-proof system ensure ML model security and privacy even as computing. Yeah. So nowadays we are seeing most of the applications are having machine learning. Right? For ML systems that require absolute security guarantees, quantum cryptography provides level of protection impossible with classical these methods. And next, we are entering into the core quantum mechanical principles. Okay, so the first one is one moment.
Karimullah sir, you are muted, sir. Please unmute yourself and start.
You able to hear me now? I'm back. So we are just into this core quantum mechanical principles. Okay. So the core quantum mechanical principles are the first one is the uncertainty principle. So Heisenberg initial principle states that the certain pairs of properties of position and momentum cannot be simultaneously measured with perfect precision. Like I mentioned before, so while in the theory of quantum, inside the atom we have these photons and those cannot be the position of that photons cannot be identified, right? So that is the statement which reveals in the state that certain pairs of properties like position and momentum cannot be simultaneously measured with perfect precision. In cryptography, when an eavesdropper attempts to measure a quantum state, they unavoidably disturb it, revealing their presence. So that is also we discussed in cryptography when the hacker is trying to eavesdropper are trying to manipulate the position of photon in the transmission media without disturbing that particular photon that cannot be manipulated. Okay, and the next one is no cloning theorem. And the principle of quantum mechanical core, there is one more foundation, that is no cloning theorem. The cloning is nothing but exact copy of that particular instance. So here, the no cloning theorem proves it's impossible to create an identical copy of an unknown quantum state without disturbing the baseline. And the security implication here is an eavesdropper cannot make perfect copies of quantum information being transmitted without leaving evidence of their interference. For example, from the source to the destination, if zeros and ones are transmitted in a bit format, and when eavesdropper is trying to he was trying to manipulate that zeros and one transmission data without evidence of that particular. And core quantum mechanics of the foundation of the principle is no cloning theorem. I hope my screen is visible now. Okay, so I'm continuing on the part. So the no cloning in the sense we cannot create an identical copy of an unknown quantum state without disturbing the original. Here is the security implication, and eavesdropper cannot make perfect copies of quantum information being transmitted without leaving evidence of their interference. This creates a powerful foundation for tamper-evident communication channels essential for secure ML model deployment. Not only this is not only for a secure ML model deployment. This is for wherever tampering occurred to get the sensitive information. Where is no cloning theorem strongly give us the secure communication need and source to destination. And the third principle is quantum and entanglement. Quantum entanglement is nothing but the two atoms or two photons which they are transmitting. They will have the connectivity even though when you place from the long distance. For example, quantum entanglement creates correlated quantum states where measuring one particle instantaneously affects its entangled partner regardless of the distance. And cryptography, in a cryptography application, entanglement particles can be used to create correlated random keys at distant location and detect if any quantum channel has been compromised. Okay. ML engineers can leverage entanglement to create secure multi-party computation system for distributed monitoring. This is the third quantum. This is the third quantum cryptography protocol, quantum entanglement. And here we can discuss about the classical versus quantum cryptography differences.
Karimullah sir, you are not audible, sir, and your PPT is also not visible.
কি
মানে সেই কাপোৰটো যে এইখন বহুত ভাবি
Sorry, I'm getting calls actually back to back. Sorry for that. So, I'm just resuming this.
Karimullah sir, sorry to interrupt you.
Uh,
So now PPT is visible, sir, but the voice is little low, sir. Could you please?
Now, is that audible now?
Now it is okay, sir. With this tempo, it is okay. Thank you.
Okay. Okay. Thank you. So, I'm just resuming the differences of classical cryptography and the quantum cryptography. So, in classical cryptography, security is based on computational hardness. Means as we discussed, the cryptography made use of zeros and ones based. And here in the quantum cryptography, the security based on loss of digits, transmitting the information and from up photons to any other medium. And in classical cryptography, it's vulnerable to advances in computing power. Means, for example, the quantum computers will break RSA algorithm seen in history. And here resistant to arbitrary computing power and cannot detect eavesdropping in classic quantum classic cryptography. And here in quantum cryptography, eavesdropping always detectable because if someone is trying to alter the transmission of photons to the medium, it will get notified to the source and destination. So here in classical cryptography, keys can be copied without detection. And in quantum cryptography, quantum keys cannot be perfectly copied. So, as we discussed, threatened by quantum computing advances in classical cryptography, in quantum cryptography, secure even against quantum computers. Okay. So next, quantum key distribution. So this is the major stage in quantum cryptography. Here, this is the feature of quantum cryptography. Quantum key distribution is a method that uses quantum mechanics to establish a secure encryption key between two parties, typically referred to as an alias bomb. Everyone knows like about the alias bombs in our strategy, like is a for example called the bomb. So QKD does not encrypt the actual message. Okay, so in AES or RSA, so we just used to encrypt the actual message or the sensitive information in ciphertext. Okay, but here in QKD does not encrypt the actual message, and it generates and distributes secure encryption keys that can then be used with semantic encryption algorithms. The primary advantage of this quantum key distribution is if an eavesdropper is nothing but whoever is listening or trying to capture the sensitive information which is transmitting to source and destination. So eavesdropper is a kind of hacker, attempts to intercept the quantum key. Their measurement distribute the system altering Elias and Bob to describe the compromised key. Means, as we discussed, wherever eavesdropper comes into the picture while transmitting the data from source to destination, then the source Alice and the Bob at at the destination, they get notified about the keys were compromised, which are being transmitted from source to destination. So this is a powerful feature in quantum cryptography. By using this quantum key distribution, we can securely share the keys which are required to be uh, get share the sensitive information. And there are a few protocols, which we need to discuss in quantum cryptography. One is BB84, the first KQD protocol. So this quantum key distribution where worked upon few protocols using few protocols. So this BB84 was developed by Bennett and Rash in 1994. BB4 was the first KQD protocol and remains foundational. So the protocols, like HTTP, HTTPS protocols to get any information or resources which are running in a server, right? So the same way, the QQT will also work on few protocols. So one of the protocol is BB84, this implemented by Bennett and Rashad in 1984, and still now also it remains foundational. It uses the polarization states of photons to represent bits with the two possible measurement bases. Correct? So polarized states from the source side and the destination side. And the source side, if the keys were transmitted with polarized states of photons to in a byte representation, and it can be measured based upon rectilinear and diagonal. A rectilinear is nothing but how can I say plus symbol, the pipeline character, and diagonal we can say like forward slash or backward slash directional, and the diagonal will represent the diagonal. The security comes from the fact that measuring a photon in the wrong basis destroys its original polarization state and produces a random result. Means, for example, when a hacker or third parties was trying to alter the state of the particular photon which is transmitting from the source to destination, I think produce a random result irrespective of the normal functionality, means normal flow. Okay, so BB84 demonstrates how quantum indeterminacy creates a communication channel that inherently reveals ever-dropping atoms. So here, ever-dropping atoms can be detected using this BB84, this quantum key distribution using this BB84 protocol. So how internally BB84 works? Step one, quantum transmission. So LI sends photons polarized in randomly choosing bases externally or diagonally representing zeros and ones. For example, if LI tries to share the information which is the form of zeros and ones, and the measurement should happen at Bob's side. The Bob measures each photon using randomly chosen bases. Means sometimes it will transmit through rectilinear and sometimes it transmits through diagonal direction. Sometimes matching LA's choice, sometimes not. So the measurement should happen perfectly from the Bob side. If the transmission of the photon is matched and some of them are not matched, the not matched photons will be go to the garbage, and the photons which are matched, which are the actual values which Bob should consider. The step three, basis reconciliation. The LH and Bob publicly share which bases they used, but not the bit values, keeping only bits where their base matches. So the from source side and from the source side, the for example, the source side, the zero is coming, and from the destination side, it should also check for zero. If it is not zero, then share that value to the garbage. Garbage is not the garbage value. Means like we are not going to consider that value. So if it is matches with the zero, which is coming from the source, then keep the value zero. And if it is coming as one and that is not shared by the LAs from the source side, then we just send that to their base. That is what the basic basis reconciliation. So, and error detection. There are subset of matching bits to check for errors of ever dropping by comparing values. So when a ever dropping comes, means that someone was trying to alter the value which is coming from source to destination. And the fifth one is key distillation. If error rate is accountably low, they perform privacy amplification to produce a final secure key. So if no error rate means no ever traffic is present, then the final secure key will be reached to the BOP at the destination site from the source. And this is how this BBA works. So how we can advancement this KQD protocols using this means this KQD protocol advancements are E91 protocol 1 and B92 protocol continuous variable KQD and measurement device independent KQD. So E91 protocol, this is also one of the protocol to create a strong secure channel from source to destination to transmit the information securely. So here E91 protocol uses entangled photon pairs offering security based on Bell's inequality violations, particularly useful for distributed ML systems that require synchronized random number dimension. So the B92 protocol, where is a simplified version of BB4 using only 2 quantum states instead of 4, optimizing implementation in resource constrained environments. And whereas continuous variables KQD uses quantum properties of light like amplitude and phase, compatible with standard telecom equipment and then longer transmission distance. So continuous variable KQD uses quantum properties of light like amplitude and phase, and then it will transmit. And measurement device independent KQD eliminates all detector. This particular protocol advancement will eliminate all detector side channel attacks, addressing a major vulnerability in particular KQD implementations. And there are advantages of quantum key distribution for ML systems. One is probable security and reverse dropping detection, forward security, and continuous key replacement. So, probable security, the quantum key distribution offers information theoretic security guarantees that don't depend on computational hardness, assumptions, protecting sensitive ML modes and data. So here, probable security is nothing but, for example, when you try to share a key from source to destination, it offers information theoretic security, and it guarantees that don't depend on computational hardware assumption. Just transmit this key from source to destination without reverse dropping. So the second one is reverse dropping detection. Any interception attempt physically alters the quantum states, allowing the immediate detection of security breaches during model training or deployment from source to destination. And forward security, here keys cannot be recorded and decrypted later with more powerful computers, ensuring long-term protection for valuable ML intellectual property. And continuous key refresh. Quantum key distribution systems can continuously generate a new key, allowing frequent key rotation for high-value ML interpretation points. In machine learning, the quantum key distribution will provide all this provide probable security and reverse dropping detection, forward security, and continuous key replacement. The real world quantum key distribution implementation Yeah. So in real world quantum key distribution implementation, so the fiber-based quantum key distribution. The quantum key can be distributed using fiber optic cables. Uses existing fiber optic infrastructure to transmit quantum states currently limited to approximately 100 kilometers without quantum repeaters. And the free space QKD. The quantum key distribution can be happen through free space. Transfers quantum states to the air or vacuum, enabling satellite-based quantum networks for global secure communication from to enter the world using free space and chip-based quantum key distribution. So this is one of the implementations where we can transmit the keys using chip-based. The system on photonic integrated circuits, potentially enabling quantum secure for HML devices, and can use commercial systems. ID Quantity, Toshiba, and others now offer commercial KQD systems for enterprise security applications. So the most secure implementation is fiber-based. I can say why the fiber-based quantum key distribution is more secure means the fiber optic cables through the fiber optic cables, so the transmission of these photons and transmission of photons can be the state which is shared from the source to destination will always equal to destination. So, for example, if someone trying to hack the particular key, then they must have to alter the position of that particular photon. If that particular photon or the particular photon is altered or trying to tamper, then that cannot be reached to the destination as the source end. Then we can know like okay, this is not the correct key. There are there is a chance someone is trying to alter the photon which is transmitted through this media. Unlike this free space QKD also was tested by one of the organizations to transmit the keys over the free space across the world. And current KQD limitations. So distance constraints. So quantum signals degrade with distance. So as we discussed earlier, it will be near to approximately 100 kilometers. But the quantum signal degrade with the distance. Current limits are approximately 100 kilometers in fiber without quantum repeaters. And the key rate, relatively low key generation rates, kbps rather than mbps, limit growth for high volume and data pass. Okay, and hardware requirements. So this is one of the major limitations in quantum cryptography and as well as quantum. The specialized extensive equipment necessary for implementation limiting deployment to high security environments. This is one of the major limitation QKD, quantum key distribution. The quantum cryptography beyond QKD is quantum secret sharing. Protocols that divide secrets into quantum shares requiring multiple authorized parties to random networks and record quantum networks. Infrastructure that enables quantum anonymous communication between multiple nodes. So this basically quantum cryptography beyond QKD is having two components. One is quantum secret sharing and quantum digital signature. So quantum secret sharing will work like protocols that divide secrets into quantum shares, requiring multiple authorities parties to record quantum networks. And here in the quantum digital signature, authentication mechanism with security based on quantum rather than computational hardness. So, so quantum safe cryptography. Yeah. So here we can have an alternative approach for post quantum cryptography. PQC. This is one of the algorithm. So in quantum cryptography uses quantum mechanics. PQC consists of classical algorithms very resistant to quantum attacks. So okay, before going to this, can we have a little break? Before going to this post quantum cryptography, you see. Hello, Sirajuddin sir. Can we have a break for 10 to 15 minutes?
Yes, sir, you're not visible. One more time, please.
So can we have break 10 to 15 minutes?
Yeah, yes, of course, sir, of course.
Okay.
Yes, all the participants, you can take break for 5 minutes, but don't left the meeting. Be connected, and you can have a small break. Don't left the call. Please stay in call.
Yes, I'm back now.
Sir, welcome back, sir.
Yeah, thank you, Mohammed. So is that still you are facing much noise from my side, or how it is? See, there are messages related to noise.
Yes, yes. Now there is no background noise, sir, but voice is little low. Can you speak little loud?
Actually, this facing some problem with mic, I guess, in Google Meet. I just checked before joining also. The mic 100% while I'm talking, but I'm not sure. Is still my voice is low, or
Still, it is little bit low, sir.
okay. Now, is that clear now?
Yes, sir. Little bit improved, sir.
Okay. So let me share my screen again. So a quick recap. Okay. So quick recap. What we discussed. So as of now, we discussed about the uh, quantum cryptography and what are existing cryptography mechanisms, and what are the principles of quantum cryptography, and what is the difference between classic and quantum cryptography differences we discussed. And now here the concept of cryptography, alternative approach for post quantum cryptography, which is an algorithm. Post quantum cryptography will uses a quantum mechanics. PQC consists of classical algorithm believed resistant to quantum attacks.
Sir, now voice is clear, sir, but PPT is not in full screen mode.
Okay.
Now it's everything fine, sir. Thank you very much.
Yeah, thank you. So this is NIST is currently standardized PQC algorithm based on lattice-based cryptography, hash-based cryptography, code-based cryptography, and multivariate polynomial cryptography, Ashogni-based cryptography. So there are alternative approaches to do the secure transmission of data from source to destination. These are the NIST is currently standardized PQC algorithms based on these cryptography models. So implementing quantum cryptography for ML systems. So risk one is the first thing we just need to observe is we just need to consider is risk assessment. Identify which ML assets require quantum level protection. Consider model IP, training data sensitivity, and the regular requirements. So in the terms of ML machine learning systems, so the implementation of quantum cryptography, we should consider the following aspects. Risk assessment. First, we need to do the risk assessment, identify which ML assets require quantum level protection, and consider the model IP and the training data sensitivity and regularity requirements. And the second one is we can implement using a hybrid architecture, implement quantum key distribution for key exchange while using post-quantum algorithms for bulk encryption of model for sensitive training data. And integrate with PKI, combine quantum key distribution with existing public key infrastructure to create a transition pathway rather than a complete replacement. And there is we need to one more aspect we just need to consider while implementing the quantum cryptography in machine learning as performance optimization. Use quantum derived key selectivity for critical operations while maintaining classical cryptography for less sensitive high throughput ML interfaces. So these four aspects we need to consider while implementing the quantum cryptography in ML systems. And the feature of quantum cryptography. So as we discussed, the quantum cryptography will use the transmission of keys from source to destination in form of photon transmissions like cable, media, or open air transmission. So the feature of quantum cryptography, like quantum repeaters, will extend KQD beyond current distance limitations, enabling true quantum network spanning nets. So, as we discussed earlier, so this quantum cryptography sharing of public key approximately 100 kilometers, and that is limited to when we use quantum cryptography implementation using fiber optic cables. But that will extend KQD beyond current distance limitations, enabling true quantum network spanning continents. Integrated photonics. So we'll dramatically reduce size and cost of quantum cryptographic systems, enabling deployment on edge ML devices. And quantum internet will create a global infrastructure for quantum secure communication, enabling new distributed ML with unbreakable security. So we can work towards quantum internet. Will create a global infrastructure for quantum secure communications and with unbreakable security. So physics-based security, implementation readiness, hybrid approach. These are the key takeaways for this quantum cryptography. So physics-based security, quantum or cryptography achieves security through the laws of physics rather than computational difficulty. And implementation readiness. KQD systems are commonly commercially available today, but have practical limitations in distance and key rate. And there is a hybrid approach, combine quantum and post-quantum techniques for comprehensive ML system protections. So these are the key takeaways in this one. And these BB84 and D91 protocols we already discussed. This presentation of explorers the foundation of quantum cryptography through the BB84 and D91 protocols. So these all are like our HTTP, HTTP4 protocols to implement this quantum key distribution QKD. And these methods revolutionary secure communications by leveraging the fundamental properties of quantum mechanics. The quantum advantage in cryptography. So the advantage of quantum. The classical cryptography relies on computational complexity, while quantum cryptography leverages the fundamental properties of quantum mechanics. So these theorems we already discussed, no cloning, and we cannot create an exact copy or identical of identity of particular photon transmission from source to destination. And no cloning theorem prevents copying of unknown quantum states, and measurement distributes quantum systems in detectable ways. For example, from the source side, if zero transmits and destination zero, the destination side, the destination should consider only zeros. So if it is one, then send to the garbage. So, and the quantum entanglement creates a correlation that can't be explained by a local hidden variables. And security derived from physics, not computational assumptions. The BB84 protocol is the first quantum key distribution method developed by Charles Bennett, and this is also this already we discussed. The BB84 protocol is used to implement the quantum key distribution. This is one of the method to share the keys from source to destination securely. So BB8 keyboard distribution step by step. This is already we discussed. This uh, the practical implementation of polarization encoding. The common implementation uses photon polarization states, horizontal 0 and vertical 90 degrees for rectilinear basis, diagonal 45 degrees and anti-diagonal 135 degrees for diagonal basis. Single photons carry quantum information between parties. Parties from source to destination, the source to destination are here are the parties. So when you say transmission of horizontal 0 degrees and vertical 90 degrees, this we can call as a rectilinear basis, and when it transmit diagonally 45 degrees and anti-diagonally 135 degrees, for this is we can call it as a diagonal basis transmission. So single photons carry quantum information between parties. The photons will carry the quantum information between source and destination. So BB4 protocol implementation often use specialized hardware, including single photon sources and detectors, and we can say like phase modulators and interferometers, and polarizer controllers and beam splitters. So BB84 protocol implementation often uses all these special hardware. So eavesdropper detection in BB84, eavesdropper intercepts even. So eavesdropper cannot, as we discussed, cannot change the state of that particular photon, which is transmitted from source to destination. This is eavesdropper. Why they are not able to intercept means, so when, for example, 0 is coming from the source side and the destination side, we should also expect the 0. It's not 1. So there are measuring techniques which are at destination side, and those will keep on trying to get the value which is shared from the source. For example, if it is 0, that would expect 0. So if someone eavesdropper is trying to capture the information, that can be alerted to source and destination. That cannot be altered. So how that will happen in BB84? This is the eavesdropper intercepts and measures qubit sends from alias to Bob. Error detection. Alias and Bob detects error by completing subset of their key and force-based choice, qubit regeneration, and quantum distribution. So by using all these techniques, we can detect the eavesdropper. So there is one more protocol other than BB84. This is a E91 protocol, quantum cryptography using entanglement. So this E91 protocol offers a profound security advantage. The security is based on fundamental non-locality of quantum mechanics and can be verified through Bell's inequity tests, making it particularly robust against certain advantages of attacks. So this is one more protocol to implement the quantum cryptography using it uses entanglement. Quantum entanglement, the foundation of E91 the protocol. This quantum entanglement is the foundation of E91 protocol. So the correlation persistent regardless of separation distance. This was we can see in the physics, like this cannot be used for faster than light communication. Means this cannot be transmitted as light from the source to destination. Provide basis of E91 security guarantees. So we have seen BB89 that protocol step-by-step process. Here also the E91 protocol, how it works. So entangled pair creations. Source creates a pairs of entangled particles distributed to Alice and Bob and independent measurements. Alice and Bob each measures their particles using randomly chosen bases. And basis comparison. Alice and Bob publicly announced which bases they used, not results. Means they used how it is diagonally or interactly, how they been shared this public, they can publicly announce basis comparison. And the key generation results from compatible measurements from the secret key. Key generation will be based upon the compatible measurements from the secret key. And the Bell test verification subset of results used to verify entanglement through Bell's inequality. So this is all about E91 protocol process follows. The combination of Bell's theorem and E91 security is the mathematical foundation for E91 security. So Bell's inequality distinguishes quantum entanglement from classical correlation. So if you say in the E91 protocol, Alice and Bob check if there are measurement statics volatile Bell's inequality. Violation. For example, if you was or someone the hacker, if they try to change or the state of that particular photon which is transmitted from Alice to Bob, the violation quantum entanglement intact communication secure. So if it is no violation, potential was dropping, it is discarded. If it is violation, then it is captured and then it is notified to the parties. And if there is no violation, it will that key will be discarded. Potential was stopping happen, and then that key will be discarded. So here is the protocol comparison, BB84 versus E91. So BB84 is simpler, requires single photon source and detectors. When it comes to security foundation, BB84 no cloning theorem and measurement distributions, and based on Bell's theorem and quantum non-locality. And when it comes to source independence, BB84 trust required in quantum state preparation, and E91 is device independent, security possible with proper implementation. This is the comparison about the protocols which we are used to implement the quantum key distribution in quantum cryptography. And the E91 is more complex, requires entangled photon sources and maintaining entanglement. So here is the security analysis. So photon, so vulnerabilities and countermeasures. So for example, if photon number splitting attacks when using attenuated lasers, then Deca state protocol to detect photon number splitting. And when it comes to side channel attack on implementation hardware, then measurement device independent KQD protocols. So detector blinding attacks exploit hardware limitations. So carefully hardware implementation and testing. So man in the middle attack during public classical communication, then authentication of classical channels of communication may help to be considered violent. This is efficacy comparison, practical KQD implementation. The the color represents the BB84 protocol users, and the E91 represents this color. So BB84 currently offers practical advantage in key rate, distance, and quantum bit error rate, while E91 provides stronger theoretical security guarantees at the cost of implementation complexity and reduced efficiency. So this is the BB84 is more reliable while implementing this quantum key distribution in quantum cryptography compared to E91 protocol. So here the detection and privacy amplification, error detection and privacy amplification. So how we can do this error detection and privacy amplification is first error detection. Alice and Bob publicly compare a subset of their shifted keys bits to estimate error rate, quantum bit error rate. Above threshold indicates potential eavesdropping. So later on, once the error detected, error correction using protocols like Cascade or LDPC boards, Alice and Bob correct errors in their keys without revealing the entire key, maintaining security while ensuring identical keys. And then later privacy amplification. Final step reduces any particle information or the particular information or partial information, and eavesdropper might have gained uses hash functions to compress the reconciled key, exponentially reducing EVS knowledge. So this privacy amplification final step reduces any partial information that is lost, and the eavesdrop may know. So the privacy amplification we should do to reduce the risk. These post-processing steps are essential for both BB84 and E91 protocols, transforming a partially secure raw key into a highly secure final key, usable for cryptography applications. Okay. So next here we have integration with classical cryptography. So this is this we can call it as hybrid crypto systems. The quantum key distribution is typically used within a hybrid system that leverages the strengths of both quantum and classical cryptography. So classical cryptography, we know we can use symmetric encryption. AES uses quantum divided keys. That keys can be shared to the parties to exchange the data. And KQD provides secure key exchange. And system encryption, AES uses a quantum derived keys. And this authentication uses quantum resistant algorithms to authenticate the user or whoever the party who is authorized to get the data. And key rotation policies benefit from KQD continuously key generation. Key rotation policies benefits from KQD's continuous key generation. This is all about hybrid crypto system. This hybrid approach offers the best of both quantum security and classical efficiency of bulk data encryption. That can be doable like a practical deployment with the existing infrastructure which we have. Ready? So in the real world, this is like a real world quantum key distribution implementation. So China's quantum backbone, 2000 plus kilometers quantum network connecting Beijing, Shanghai, and other cities, demonstrating large-scale KQD deployment using both fiber and satellite links. As we discussed earlier, this quantum key distribution implementation it can be done by using fiber optics and by using open air. That is nothing about satellite links. So China quantum backbone was describing 22,000 plus kilometers quantum network connecting Beijing and Shanghai and other cities, demonstrating large-scale KQD deployment using both fiber and satellite links. They are implemented using fiber optics and satellite links. And Mickey's quantum satellite, the world's first quantum communication satellite, established intercontinental quantum secured video call between China and Austria using satellite relayed QPD. So in the both areas. And financial sector applications, several banks in Europe and Asia have implemented KQD for secure transmission between headquarters and data centers, protecting financial data transfers. So this KQD implementation is already there, and it is tested in China's quantum backbone, and as well as and some financial sectors in Europe were using this quantum key distribution. So as of now, we have seen this implementation was done using fiber optics and the satellite using the satellite links in the real world. So quantum networks are the next context. The future quantum communication infrastructure will be expand beyond point-to-point KQD to full quantum networks, offering unprecedented security and capabilities. So quantum networks are nothing but like we are how can I say it? This is a kind of network. It offers to share the quantum keys over the network, and that is a kind of platform, software as a service, platform as a service, and here is a network as a service. And quantum computing. It will offer this network will offers to share the quantum keys over the network to the large area. I mean, so it will cover the large areas. So quantum repeaters to extend range beyond current, limitations multi-user quantum key distribution with optimized routing, quantum memory for storing entangled states. These networks will form the foundation of future quantum internet, enabling application beyond just secure key distribution. As I mentioned, these networks will form the foundation of a future quantum internet, enabling application beyond just secure key distribution. Not only key distribution, it may offer many quantum networks may offer many other features also. Challenges for large-scale deployment: distance limitations, period bottleneck, standards and certifications, hardware costs. So these all are limitations when it comes to large-scale deployment. Key takeaways. These already we discussed: quantum-powered security, complementary approach, real-world applications, quantum feature, evolving technology, hybrid architecture. Yeah, this we already discussed. These all are the key takeaways, and we already discussed about the most key takeaways already, which are here. This is all about the key takeaways of quantum cryptography, and here are the final key takeaways. Quantum powered security will use this BB84 and E91 protocol, leverage quantum mechanics to provide security guarantees impossible with classical cryptography. And the hybrid architecture, evolving technology, quantum feature, real world applications, complementary approaches. So these all are key takeaways which we will discussed. So I'm just stopping my screen sharing. So before going to our the other topic. So this is on quantum cryptography principle and tech. This is all about this quantum cryptography principles and techniques. There is one more topic that we discussed in the session before. That is about this one. You can say the post quantum cryptography. post-quantum cryptography essentials. So this is the next topic which we are going to discuss. Okay, so before going to that one, before going to that session, the session 4, we can have 5 minutes of break, and we can connect at 8:05 p.m. again back. Rajatin, sir, is he there?
Yes, sir. Yes, sir.
Yeah, so the topic of quantum cryptography principles and measurements covered. So there is one more session just wanted to present.
Okay, sir. Do you want to have any break?
Yes, yes, 5 minutes of break for all the participants, then we'll come back. Means rest of, I will be in the call itself, and we'll be back in 5 minutes.
Okay,
So
sure,
that
sir.
is, so we can combine this, like no need to join in other sessions. So this we can continue in this session itself, right? For
Yes,
that
sir.
topic
Yes, sir.
also.
Yes, sir. No need to disconnect.
Okay, okay. Thank you. We'll be back
Thank
in
you.
5 minutes.
Okay. All the participants, please be connected, but you can take the break. Thank you very much. Don't leave the session. Just you can have some break.
So, hi everyone, I am back again from the break. I'm just sharing my screen again on the second session. Just let me know once you're able to see my screen.
Welcome, sir. Please continue.
Okay. So this I just shared the different window. One moment, give me a moment.
Sir, you are muted, sir.
Yes, yes, I'm just sharing the screen. Let me enter screen that is possible. So here is the next session on post-quantum cryptography. So as we discussed in quantum cryptography, we securely share the quantum key distribution using different protocols. So here one more topic, post-quantum cryptography is the development of cryptographic algorithms that are secure against attackers by powerful quantum computers. So, for example, we have taken that quantum cryptography as a strongest mechanism to implement to share the keys to the parties securely. Rather, we use the classic cryptographic method like AES, RSA, the kind of. So here the PQC is a development of cryptographic algorithm that are ensure secure against attacks by powerful quantum computers. So when today's computers are too limited to break modern encryption like RSA and ECC, future quantum computers using algorithms like Shor's algorithm will be able to do easily. So to prepare for the quantum threat, so we just need to implement. We need to use this post-quantum cryptography essentials. So the agenda is to understand the quantum threat, quantum computing fundamentals, timeline of quantum development, Shor's Groves algorithms, how these algorithms, the set of rules were intended to crack the sensitive information, and post-quantum cryptography, the mathematical foundations, NIST standardized process, key algorithms, families, and implementation strategies of this post-quantum cryptography, migration of approaches, performance consideration, integration and challenges, and the action plan and the timeline about the crypto ability, the agility framework, readiness assessment, and phased implementation. So these all are the agendas for this post-quantum cryptography mechanism. The quantum thread basically use the Shor's algorithm and Groovy's algorithm. So the Shor's algorithm, okay. Before getting to the those algorithms, let me in the why this matters. So our entire digital security infrastructure relies on cryptographic problems that quantum computers will eventually break. So as we discussed with an example, like in any of the application, we have different sensitive information we need to deal with. So the quantum computers will eventually break the particular transmission of secure data using different algorithms. So 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 why basically this is matter the coming crypto collapse. So, for example, if you decrypt the particular ciphertext, you will get the actual message, which classic cryptography mechanism is. So, attackers are already underway. Sensitive data with long-term value is being collected today to be decrypted once quantum computers are capable. As of now, the quantum computers are capable, but that is not live. So, in future, the quantum computers are really capable to break the secure mesh which we implemented in any of the applications or any of the real world examples. So it took 25 years to deploy our current public key infrastructure, but we may have only 10 to 15 years to replace it by using this PQC. So understanding of classic cryptography. So as we discussed earlier, before we discussed quantum threads, let's review how our current encryption system works. So symmetric encryption. This is most often we are using same key for encryption and decryption. Example AES ciphertext. So ciphertext is not human readable, but the actual message is human readable. That we are just converting that to ciphertext, and then we are make use of it for transmitting the sensitive information like keys and all. So the key distribution problem, how do we share the key by using secure symmetric key encryption that we can discuss, and asymmetric encryption where we can use IRC algorithm, RSA and ECC, these two algorithms, why we can achieve this asymmetric encryption, and the hash functions. One way function that produces fixed length outputs used for digital signature message identity verification. For example, when you are logging to when you are logging to any of the site or um, any of the uh, government sites where we have this digital signature verification for any of the what I can say, like the forms and all. So these all are the classical cryptographies which we are currently using. So asymmetric encryption, which is wisely using in current real time in real world current applications. So the actual message will be converted to the ciphertext, and then the ciphertext will be decrypted by using any of the base64 encode or decode. And asymmetric encryption uses mathematical related key pairs, example RSA tokens and ECC, so that they can be securely transmitted, and the hash functions. So this is a fixed length of outputs for each of the key. We have a hash code that by using that hash code we can get that particular value. These systems form the backbone of our entire digital security infrastructure as of now, from secure browsing to digital transition to secure communications. Okay. And next, the quantum computing threat model. Yeah, the threat model involves these two algorithms. Source algorithm implemented in 1994 and Lewis algorithm 1996 can efficiently solve integer factorization problem, breaks RSA. It will break the RSA token. It will get the RSA token source algorithm. And discrete logarithm problem breaks ECC.
Sir, sorry to interrupt you. Can you make full screen of this PPT?
Yes. Okay. That is actually I'm presenting in PDF mode. So
okay, sir. Now it is visible, sir. Okay, thank you.
I just zoom in. Just let me know if it is.
Yeah, now it is visible, sir. Clear now.
Okay. So the quantum computing threat model involves these two. The threat model will have this source algorithm and Guru's algorithm. What it will do, it will break the RSA. The source algorithm will break efficiently. They solve the problem of the breaking of RSA, getting the RSA token, and discrete logarithm problem breaks ECC, DSA, DHA. Effectively breaks all widely deployed public key cryptography. algorithm, basically the Shor algorithm. And the Groovy's algorithm provides quadric speed up for search problems, reduces security of symmetric encryption. AES 128 effectively becomes AES 64, mitigated by doubling key sizes. The most immediate and severe threat is to our public infrastructure, which secures everything from HTTPS to VPNs to digital signature. So what we are currently using, for example, any of the resource which is running inside the server or any of the cloud environments, we used to get that resources using HTTPS protocols. If you want to secure that particular resource, we just have to follow some cryptography mechanisms like AES or the RSA tokens and other stuff. So that can be breaks. It will break. It means the problem. Whatever the encryption decryption or cryptography mechanism which we used, that can be solved by using the source algorithm and Groovy's algorithm. And our secured resources can be accessed to HTTPS protocol over HTTP. So HTTP, it's not secure. HTTPS means it's secure. And if you want to get unauthorized access to any of the resource which is within the organization, we can implement the VPNs to get the digital signature granted for that particular resource. So these two are the source algorithm and Groovy's algorithm. Are these two algorithms we can effectively use to get the problems which are arising while sharing. The quantum timeline, when it will happen. This is the history all about this. We can get it actually, and this is not. And what is post quantum cryptography? This is what the main motto of this particular session. The post quantum cryptography refers to a cryptographic algorithms believed to be secure against attacks from both classical and quantum computers. It's a kind of hybrid computing mechanism. So post-quantum cryptography will algorithm believed to be secure against attacks from both classic and quantum computers. These algorithms rely on different mathematical problems that quantum computers cannot efficiently solve, even with Source and Groovy's algorithms. So we discussed the Source and Groovy algorithms will resolve few problems which are currently exist, but these algorithms rely on different mathematical problems that quantum computers cannot efficiently solve. The key characteristics of post-quantum cryptography are based on math problems resistant to quantum algorithms, implementable on existing classical computing infrastructure, and designed to interoperate with current protocols and networks, focus on maintaining security while optimizing performance. So there are Shor's and Groovy's algorithm. It will solve a few of the problems which are existing, and quantum cryptography, post-quantum cryptography will capable of doing below means below characteristics. It will work on below key characteristics. These characteristics. So post-quantum versus quantum cryptography. The quantum cryptography, the last topic which we discussed, that we can transmit the quantum key distribution over fiber optics or air through air, open air. So here are the difference between post-quantum versus quantum cryptography. Post-quantum cryptography is math-based solution, runs on a classic computers, works with existing infrastructure, algorithmic approach, focus on NIST standardization. So quantum cryptography is a physics-based solution. As we discussed, photon will be transmitted through the media. That media will be like a fiber optic cable or the satellite, and it requires specialized quantum hardware, and it is more cost effective, and it needs quantum channels like fiber optics are based and the quantum cryptography based on quantum mechanics principles limited to key distribution. This is limited to key distribution, the quantum cryptography basically. This is focus on NIST standardization. Our focus today is on post-quantum cryptography as it offers the most practical path forward for organization to secure their system against quantum threats. So once the quantum computers are fully operated, then any of the ciphertext or any of the RSA, any of the CCS will be cracked. Right, the quantum computer is having a probability that, but our focus is today on post quantum cryptography as it offers the most practical path forward for organization to secure their system against quantum threats. Yeah. So this is National Institute of Standard of Technology begin a process. This is the necessary of NIST PQC standardized process. That is not required. The five families of PQC algorithms. Post-quantum cryptography algorithms are having this families lattice-based, code-based, multivariate-based, hash-based, isogeny-based. So lattice-based, based on the hardness of finding closest vectors in high-dimensional lattices. So this family of algorithm, lattice-based algorithm, examples crystal, Kyber, crystals, deuterium, nickel, Falcon, having pros of good performance and well studied, and code-based, based on the difficulty of decoding random linear codes. This is classic MLI's bike. So the pros are longest studied PQC approach since 1978. So this was code-based was the longest studied PQC compared to other families actually. And multivariate based on the difficulty of solving system of multivariate polynomial equations. And this hash based solely on the security of cryptographic hash function, and isogeny based on finding paths between elliptic curves. Deep dive into the lattice-based cryptography. So lattice-based cryptography has emerged as the leading approach for post-quantum security. So why it is leading means lattice cryptography provides excellent performance characteristics while maintaining strong security resilience against both classical and quantum attacks. So for classical and quantum attacks, lattice cryptography provides excellent performance characteristics while maintaining strong security resilience from source to destination when we are sharing the information, sensitive information. So that is based on the shortest vector problem and learning white errors, and offers good balance of security, key size, and performance. And its secure relies on the difficulty of finding the closest vector in the lattice. And the PQC algorithm comparison, this is the crystal cable lattice. This the performance comparison of different families of PQC. Okay, and the implementation challenges of PQC. So implementation challenges of PQC are like protocol compatibility. While implementing the PQC, many existing protocols have hard-coded assumptions about key sizes and cryptographic operations. And security uncertainty. The PQC algorithms are relatively new compared to battle-tested classical algorithms. So the impact would be ongoing cryptanalysis may reveal weakness, required algorithm updates. And performance overhead. Most PQC algorithms are more computationally intensive than current cryptographic standards. Potential latency increases, higher CPU utilization, battery drain, and mobile devices when it comes to the hardware. So hybrid cryptography, a transitional approach. Given the relative networks of PQC algorithm, hybrid approach offers the best security during transition. So combining classic and post-quantum algorithms in a way that can be securely. Yeah. Provide defense in depth against both classical and quantum attacks. The hybrid cryptography will help to provide a different to maintain a backward compatibility while adding quantum resistance. And these protocol impacts and standardization. So there are a few protocol impact on standardization. TLS, HTTPS, SSS, SFTP, Secure File Transfer Protocol, and PKI, MMI, PGP. So Chrome and other browsers experimenting with the hybrid key exchanges. Certificate size increases may require TLS protocol adjustments. And when it comes to SSS, SFTP, OpenSSH 9.0 includes hybrid PQ key exchange, uses NTRU prime, and by default since 2023, backward compatibility mechanism already in place. For MME, MIME, and PGP, RFC routes for hybrid signature schemes, significant client software updates required. On the standardization impact protocol, many standard bodies are actively working on incorporating PQC algorithms, but the transition will take several years across all protocols. So they are still in implementation phase. Case study, Google's PQC experiment. So Google has already implemented this post quantum cryptography in 2016, and here are the key findings. So median connection latency increased by only 20 milliseconds, and the CPU usage increased by approximately 1 to 2%. TLS handshake size increased by 5 to KB. No major compatibility issues detected. Google has since continued with experiments using NIST selected algorithms, so which we discussed before. The foundation of EQC migration. So crypto agility is the ability to rapidly transition between cryptographic algorithms, and without significant system changes, a critical capability of PQC migration. So what we should do, cryptographic inventory, catalog all cryptographic assets, algorithms, libraries, and dependencies across our enterprise, and abstraction layers, implement cryptographic abstraction layer that separate algorithm implementation from application logic to secure the sensitive information, and the parameterization, ensure cryptographic parameters are configurable rather than hard-coded. Means basically, let's say if you have a parameter that has to be dynamically added at runtime, we just ensure that we are not hard-coded that particular parameter. Instead of parameters are configurable rather than hard-coded. We can pass the cryptographic parameter value at runtime and runtime selection. So enable system to negotiate and select appropriate algorithm during runtime. Means like loose coupling. Like instead of having a runtime, instead of having a selection of algorithm statically, so we can select the algorithm which we require at runtime. Update mechanisms, establish process for regular cryptographic updates across the enterprise. So that is about this PQC migration from the other, for example, quantum cryptography. PQC implementation strategy, phase 1. So this is the complete implementation strategy, which the best practice we need to follow while implementing the PQC. The phase 1 assessment now, inventory cryptographic assets, identify high value data requiring long-term protection, evaluating existing crypto agility, build awareness and technical expertise. And in phase 2, preparation 1 to 2 years, implement crypto agility frameworks, test PQC algorithms in non-production, like in lower environments, and update PKI planning, engage vendors on PQC roadmaps. And phase 3, hybrid deployment. So hybrid deployments are since hybrid classical and PQC solutions simultaneously and prioritize long-lived data systems, update key management system, and establish monitoring for algorithm duplication. And in phase 4, full transition plus 5 years, complete migration to PQC algorithm, decommission vulnerable classical system, maintain crypto agility for future transition. This is all about post-quantum cryptography implementation strategy, which we need to follow, which we have, for example, if we need to um, decommission the existing classic cryptographic mechanism which we are using in our at our enterprise level. So this is how we can plan the PQC implementation strategy in any of the enterprise. So getting started your PQC action plan, immediate action next 20 days, form across functional quantum. This is just like a plan to decommission the existing cryptographic mechanisms which we are using to replace with the PQC. So immediate action we should do is form cross functional quantum readiness team with representative from security, infrastructure, application development, and compliance. Complete an inventory of cryptographic assets, focusing first on system protecting high-value, long-lived data. So here, the high-value, long-lived data is nothing but sensitive information like conditional strings and other the code standards and code practice, based code practices, and all. So evaluate current cryptographic libraries for PQC support and update plans. Develop a quantum risk assessment framework for your organization. It's like a utility that we can make use of the same framework in a entire organization. Begin technical training for security architects and cryptography specialists. So this is the action plan before you want to start working with PQC. So these are the latency hash-based and multi-rate approaches to post-quantum cryptography for technical decision makers preparing for quantum-resistant infrastructure. So post-quantum cryptography is the next generation algorithm to secure tomorrow's digital world. The quantum threat landscape. Why we need quantum resistant algorithms? So Shor's algorithm running on a sufficient powerful quantum computers can factor large integers and compute discrete logarithms breaking RSA, DSA, ECC, and Diffie-Hellman. So harvest now, decrypt later. Attack mean encrypted data collected today can be decrypted once quantum computers becomes available. As of now, the quantum computers are not available, so we are continuing with the current approaches. But once this harvest now and decrypt later attack means it will happen means that once it will be captured now, the data will be captured now, and tomorrow it will be decrypted once quantum computers become available on the same sensitive information. So the quantum threat landscape is that it will capture now and then reveal tomorrow. And this one. Understanding post-quantum cryptography. What is post-quantum cryptography? What it is? Cryptographic algorithms believed to be secure against attacks from both classical and quantum computers. It's a kind of hybrid computing mechanism. Like it will support both classic and quantum computing. What it will not do? Not quantum cryptography, which uses quantum mechanics for secure communication. So it's not a quantum cryptography. It's a different kind of quantum cryptography. The goal of post-quantum cryptography is to provide the same security properties as current public key algorithms, but resistant to quantum attacks. It will also block or reject the quantum attacks. Even the quantum computers can't able to reveal the actual sensitive information. So when symmetric encryption, AES 256 remains largely quantum resistant with increased key sizes. Public key cryptography requires entirely a new mathematical approaches. Symmetric versus asymmetric PQC. Here also in post-quantum cryptography also there are symmetric and asymmetric algorithms. The symmetric algorithms largely focus on securing against quantum attacks with larger key sizes. AS256 remains variable with estimated 128 quantum security, and it simply upgrade path primary key length increases. When it comes to asymmetric algorithm, completely replacement required. If it, if it is asymmetric algorithm, RSA, DSA, ECC, Differ-Hellman, all honorable. New mathematical foundations needed. Different security assumptions are proofs. So, yeah. This we already discussed: lattice-based, hash-based, multivariate, code-based, Isonagi-based. So lattice-based, based on finding shortest vectors in high-dimensional lattices. So hash-based will focus on security derived from hash function properties, and multivariate solving systems of multivariate polynomial equations. Code-based decoding problems in error-correcting codes, and it is finding this. And when we go deep into the lattice based, this is currently the most promising and widely adopted approach. It relies on the difficulty of finding the shortest vector in a complex multi-dimensional lattices. And when it comes to hash-based cryptography, it's a class of digital signature scheme that probably secure. They are a bit less flexible and they are often stateful. And meaning a new key pair must be generated for each signature. These are most key approaches for the PKC. That is based on the foundation. This already we discussed, and that is based on the crystal Kyber, crystal Digitnum, and Qualcomm. This is also discussed. So this hash-based cryptography for foundations are mathematical foundations, security based on the properties of cryptographic hash functions. One-way functions easy to compute and hard to invert, and collision resistant, difficult to find two inputs with the same output. Markle trees, hierarchical authentication structure. So this simplest PQC approach with longest history and strongest security content. Security depends only on hash function properties. So everything will be worked using a hash codes here in a hash-based cryptography. So hashing mechanism is truly the hash mechanism. And so these are the hash-based algorithms: Phoenix, CS, XMSS, LMS. So there are set of rules to be implemented while using these hash-based algorithms in PQC. And multivariate cryptography foundations. This mathematical foundation general approach define a set of multivariate quadratic polynomials. F apply secret transmission to S and to create a public key. And the problem of solving such systems is NP hard in general case. And these multivariate algorithms, rainbow, GMSS, current statuses, and this is all about the description of the algorithms, multivariate algorithms in PQC. And this is the comparison of algorithm comparison, performance comparison, so public key size, signature cipher size, operation speed, and all on the map. So when you are implementing this PQC, there is an algorithm selection criteria to be followed. So first, security, we just need to consider the security, confidence, performance, and implementation. How we can security confidence may affect the resistance to be both classical and quantum attacks. So maturity of underlying mathematical problems, and cryptanalytic security received, and conservative security margins. And the performance, when it comes to performance, we need to consider the performance also, efficiency across different metrics, computational requirements, memory usage, CPU usage, and ciphertext sizes, energy consumptions. So implementation, when it comes to algorithm selection, we also need to consider the implementation phase. Practical considerations, side channel resistance, implementation complexity, hardware acceleration potential, and compatibility with existing systems. So these all three we need to consider while selecting an algorithm. This is an algorithm selection criteria we just need to follow. So organizations should weight these factors based on their specific use cases. So every organization will have their own views. So organizations should weight these factors based on their specific use cases, security requirements, and operational constraints. A multi-algorithm approach may be necessary for different applications within the same infrastructure. If you can consider to implement this FPA. So this is the history status. Means it will with the NIST standardization status as of now. On the hybrid approach. So we just talked about the hybrid approach. Basically, every organization will have their own thoughts on post photography. While selecting the model, so you can have a hybrid approach. What is it? A combination of traditional and post-quantum algorithm is parallel so that an attacker must break both to compromise security. For example, if from source to destination, if you transmit any of the sensitive information or sensitive keys, for example, so if you follow the hybrid approach, the attacker should break the both possible implementations. Like one is the classic quantum cryptography, and the one is post quantum cryptography. And the why to use this one, provide security even if one crypto system is broken. Traditional algorithms are well understood. PQC algorithms are still maturing. And how to implement? Combine key signature from both systems. Example X2559 and K for key for the exchange and for signature. For signature, we just need to key and then deliver name for signature implemented protocol level, which we chosen while implementation the protocol. Yeah. So as an today's agenda, implementation challenges also the one of the factors we need to consent about. So one is larger key and signature sizes, integration complexity, side channel vulnerabilities, and performance overhead. The larger key and signature sizes, PQC algorithm typically have significantly larger keys and signature than current cryptography. Protocol size limitations, DNS certifications we need to install while we are working large key and signature sizes. And bandwidth constraints, storage requirements for key management. That is also we need to consider while implementation, because storage is a part of cost to the company. So we just need to implement it. And integration complexity, retrofitting existing protocols and infrastructure means to decommission the existing, and we just need to think about the existing protocols and the existing cryptography mechanisms which are there existing, and then when you are moving from the classic or the existing cryptography, so we just need to check on the integration complexity as well. And performance overhead, so most PQC algorithms require more computational resources rather like our systems. The PQC algorithm will consume more CPU and memory from the hardware, where it is running. And side channel vulnerabilities, new attack surface specific to PQC implementations, like cache attacks on large data structures, fault injection possibilities, and timing attacks on polynomial operations. So these all are implementation challenges on PQC. So, and migration strategy, the 5-phase approach, phase one inventory, like The previous session we discussed about the migration, the implementation of migration strategy. Here also in PQC, we just need to follow the strategy: phase 1 inventory, and 2 separation, and phase 3 hybrid deployment, and phase 4 transition, and phase 5 maintenance. This is something like equal to the HDLC. HDLC will just gather the requirement, and then after preparing network selection, the technology selection and implementation, and then after implementation and transition and maintenance, and this is equal to the front. The phase 1 inventory: catalog all cryptographic assets, identify all systems using a public key cryptography which are currently running, and classify by criticality and the lifespan, and document key sizes, algorithms, and certification lifetime. And in phase 2 preparation, develop cryptographical agility frameworks, lab testing of PQC implementation, performance compatibility assessments, team training, and knowledge building. And phase 3 hybrid deployment, deploy hybrid cryptography in high value systems, update key management system, monitor performance impacts. And in phase 4, shift to full PQC, remove classical algorithms when appropriate, and complete enterprise-wide deployment and maintenance. Okay, continuously monitor the PQC model which we implemented, regular security assessments, and prepare for algorithm substitution if needed. And real-world adoption examples: Google Chrome, Cloudflare. So Cloudflare, the Cloudflare is a kind of filter gateway, and requests come to a resource which is securely running in a server or somewhere in the cloud. So experimenting with the X25519 key for accurate key exchange in TLS, integrated into Chrome Canary and Cloudflare Edge servers, performance metrics, collection, production environment, minimal overhead observed in real world tests. So Google Chrome and Cloudflare are the example for adoption example, real world adoption examples. AWS Azure, post-quantum TLS option for cloud services, AWS KMS offering hybrid post-quantum key exchange, and Azure implementing PQC for internal communication between the resources. When you install or running the Azure pods or Azure Kubernetes services. So Azure implementing a PQC for internal communication between the services, both developing migration tools for enterprise customers. OpenSSH, this is also one of the adapter tool implemented NTRE based key exchange, Science version 9.0. So this will provide a real world deployment experience. OpenSSH. Yeah, okay. So here are the key takeaways. Next steps: don't wait, begin preparation now, especially for systems with long-lived data certificates. The harvest now defibrillator thread is already active. Harvest now and defibrillator. This is nothing but just to capture the sensitive information now and compute it later once the quantum computers are ready. And this we just strongly follow the hybrid approach, implement hybrid cryptography during the transition period, balance security with operational constraints. Next steps: inventory cryptographic assets, develop cryptography agility, lab test PQC implementation. This is the normal workload we can start when we are moving to PQC or starting newly implementing the PQC in our level. Yeah, that's all about the post-quantum cryptography. Yeah. So I'll give a quick recap. So quantum cryptography and post-quantum cryptography, these two are the major roles which are going to be played in digital world next years.
Thank you very much, sir.
Yeah, thank you.
Good evening once again. On behalf of Vageshwari College of Engineering, I extend my heartfelt thanks to our esteemed speaker for sharing such a valuable insights and enriching today's session. I also thank all the participants for your active involvement and keen interest throughout the program. We look forward to your continuous participation in upcoming sessions. Thank you. Before leaving this session, please give the feedback which is available in chat box, as well as attempt the quiz. Thank you very much. Thank you for your cooperation. Bye-bye. Feedback link is available in chat box. Please attempt. And we will also post in the group.